I'm Dr. J.D. Armstrong. I'm the Maui Technology, Education, and Outreach Specialist here at the University of Hawaii Institute for Astronomy. And one of the things I get to do every month is put together these talks. And this time I had no trouble finding somebody. Mark heard about the announcement for TRAPPIST-1 and said, hey, I really want to give a talk on that. So here he is. So Dr. Mark Willman, he received his PhD in astronomy from the University of Hawaii. Before that, I know he was an orchid grower over on the Big Island and had some dealings with Hong Kong, international businessmen here. And the only thing that he said to say about him is that he's a fan of habitable exoplanets. So,
thank you, JD, and welcome everybody. Tonight I'd like to talk about a remarkable discovery that's just been made in the last 2 years.
And walk into the light.
This here? Okay.
Yeah.
Let's see. It's called TRAPPIST-1, and it's a red dwarf star. Is that coming through? Yeah. About 40 light years from here, and this was a totally unexpected discovery. It wasn't certain early on that there would even be suitable planetary systems around red dwarfs. This was the first one where we've been able to observe it, and it was kind of a shot in the dark. This whole survey. People were very skeptical that they would be able to get results. They're using very small telescopes, only 0.6 meters. They have one in Chile and one in Canary Islands, and yeah, I mean, these are, amateurs have telescopes this size sometimes, very well-heeled amateurs. And so it doesn't take a 10-meter telescope to do this method. I'll describe the photometry. We measure the light output of the star, and we pick these up by the shadows they cast on the star, the dip in the light. But first, now this topic plays into an ancient question. It goes back thousands of years, at least to the ancient Greeks. Plato and Aristotle discussed this question about whether there was life elsewhere, and there's been a wide divergence of opinion on what the odds are. Are we unique in the universe? Is this the only planet? It wasn't known how many planets there were until about 20 years ago. We started discovering planets around other stars, and so the ancients had very little information to judge from. But we now know that, well, I'll give you an example. When I was a small lad, I read a cosmology book that was written much earlier, decades before, so it would be early 20th century. And it made the very strong claim that the Earth was the only place in the universe with water. And therefore, there could not be life elsewhere because there wasn't any water. Well, we now know that water is ubiquitous throughout the universe. Clouds of waters in galaxies, presumably it's everywhere. Water is one of the most common substances around. It's made out of hydrogen and oxygen, of course, and hydrogen is the most common element. Oxygen is CNO, or the next three common ones after hydrogen and helium. So there's a lot of water molecules around. So you go from that view that this is the only place life could possibly be, to the opposite view, say around the turn of the 20th century, around 1900, discovered, he thought, canals on Mars, and he took those as a sign of civilization. And there was huge interest by the public in this. There were popular magazines that had pictures of this civilization. They knew the gravity was weaker, so they postulated these high spire type buildings, and the creatures there were perceived as being very tall and skinny with wings. They flew through what we now know to be almost a non-existent atmosphere on Mars, and they generated a huge wave of excitement. Totally wrong. There are no canals on Mars. The lines Lowell was describing were optical illusions. He had a good imagination. It happens. You get it wrong sometimes. So this plays into that question. And here is Giordano Bruno, astronomy's favorite martyr. He said there are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. He said this in around 1580. So he was a predecessor of Galileo's. He came about 20 years before Galileo's career started. So that's one view. He was the first person, I think, to really make a strong claim like that. And he gets some criticism. People say, well, he didn't have experimental evidence. What was that based on? It was just another fantasy, like any claim you could make. Not really. He thought about it. He looked at the sky. He saw these stars. He looked at our sun. He knew the sun was way brighter than the planets. It was a reasonable inference, I think, that those stars might be like our sun, only a great distance away, so they're much fainter. So I would say he was basing it on evidence. It was just naked eye evidence. He didn't have a laboratory, but he drew the right conclusion. These guys got it wrong. Earth is unique. Now we know that's wrong, wrong, wrong. And so, unfortunately, Bruno came to a bad end. This was considered heretical by the church, because if there's other planets, presumably they have other gods, and then the authority of the Catholic Church would be challenged. So that was not permissible. He was burned at the stake. Now, where is our target tonight, TRAPPIST-1? Well, first of all, let's look at the name. This was the original name of the star, 2MASS J23062928-0502285. So you can see why they prefer TRAPPIST-1. Now, TRAPPIST-1, by the way, is after a beer that's brewed, or not TRAPPIST-1, but just TRAPPIST. There's TRAPPIST beer. You may see it in the market. I don't know. It comes from monasteries in Belgium, and this goes back many centuries. They were given a license to produce this beer. They're not allowed to make a profit on it. They're allowed to support themselves and do charitable works. But it's very good beer, so I hear. I can't think I've had one, actually. And so the leader of this, the PI, the principal investigator on this project, is a Belgian. So he named it after the local beer. And this name actually is informative. Now this is 2MASS. That's a very famous survey. It's the 2-micron all-sky survey. 2 micron is in the infrared range of wavelengths. So this was an all-sky survey that's very useful. It's been around for many years now. Many discoveries have come out of it. And then this is the coordinates. This is RA and right ascension and declination, the same as longitude and latitude on the Earth. This is the sky version of that coordinate system. And this is in time units. That's 23 hours, 6 minutes, 29 seconds, 0.28. And this is minus 5 degrees declination below the equator. And 2 arc minutes and about 3 arc seconds. So where is that right now? Well, here it is in the sky. It's in the constellation Aquarius. There's our target right there. This blue line is the ecliptic. That's the plane of our solar system. It happens to lie. This is totally coincidental because this is 40 light years away. It has nothing to do with our solar system. It's just a complete coincidence that it happens to be lying almost dead on the ecliptic. Where is that right now? Let's see. Last night I was prepping this and I figured it out. I think 23 hours. You can also see the coordinates here. 21 to 23 hours is the the right ascension, and here's 0, minus 5 degrees. So that agrees with the name. Right now, 23 hours would be about 2 hours from setting. Where am I? In the west. And Polaris, the North Pole in the sky, is about 20 degrees above the horizon from here. We're at 19 degrees latitude. So if you do a shaka at the end of your arm from the horizon up, that's 20 degrees. So there's Polaris. Let's come back 90 degrees from there. That'd be right there. Let's roll over to 2 hours before setting. So right now, TRAPPIST is about there. That's our target, 40 light years in that direction. Now, okay, here's the data. This is what they see. So what they do is they at TRAPPIST, and they take a picture every 30 seconds, every 60 seconds. I'm not sure what the timing is. It's a fairly small telescope. And each picture is then, they measure how much light comes out of that target, that star. And so you go along, picture, 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 picture. There's a little bumping around. This is noise. You know, the atmosphere is fluctuating. You can't So this is just random noise. So you're going along, but it's pretty steady. Then all of a sudden, bam, it drops. And it stays down low for a while, and then it comes back up. Now the coordinate axes here, this is time. So this is in minutes, 0, 30, 60. So this is about a 2-hour span. And so this dip in the curve here is about a half an hour. And then on the left side, we've got the, what's that called? Relative brightness. This is 100%. These are arbitrary settings, but the ratio is right here. So 100%, and here we're 98%. So this dip is drops about 1%. That'd be about 99% there. So we have about a shadow. When this planet comes around between us and TRAPPIST, it casts a shadow on the star, and the light dips about 1%. So now, if you know how much that light dips, then you know how big the shadow is, therefore how big the planet is. So now we have a radius measurement. Sweet. And then, what's that? I'll get to those. Give me, okay, the question is, what is the radius of this planet? Say, I'll come to that. Give me 2 more slides. I'll get to that. Now, here, and then okay, so as you notice, we've got 7 different light curves here, and this is deep, and then they steadily get shallower as you go down. Now, does anybody have any idea why the curves would get shallower? Yes, exactly. So you could have a bigger shadow, of course, or you could have beam-sized objects at different distances. And close up, it's going to be a bigger shadow. You get farther away, you're going to have a smaller cross-section. All right? So we see from deep to shallower and shallower. These are organized from close to the star to far away. And then the width of this dip, you notice this is fairly narrow, and as you go down, they get wider and wider. What does that indicate? Exactly, how long it is. So that's the distance from the star. That's the orbital period, how fast it's moving. Close in is fast. Here's one close in. The farthest one out is fairly slow. This takes about 1 hour, whereas that's about a half an hour. Okay, so there's the data. That's what this is all based on. Now here's another version of the same data over a longer period. This is the raw data from which they constructed those light curves. So here's the data. Again, we're at time here. Now this is over a period of several weeks. This is last year, September 21st. Here's my birthday, and here's 11th October. So that's about 3 weeks. We've got a run of data here, and then again on the left is the brightness. So here's 100%. There's down. There's 99, 98, and so on. So we're dropping 1%. And so we run the general, they've put this right at the mean of 1, the mean of the brightness. And then you see sometimes you get these holes, where there's a hole down below, there's been a sudden drop in brightness. So they've carefully calculated all these, and they get these, they identify each gap, and then if their planet's orbiting, they have to be periodic, right? So here's the first planet, and you see they're fairly frequent, and each one corresponds to a gap there, like that. And then you come down, and you get farther and farther away from the star, and then these are very slow. The last one here has only 1 data point, because they ran this for about 3 weeks. Its orbit is approximately 3 weeks, so we only saw it pass the star once, whereas this close one we saw it pass 2, 4, 6, about a dozen times, 15 times or so. They're doing observations right now that'll be released in about 2 weeks. And that should nail down this last planet. We should get the orbital period more precisely. But it's approximately 20 days. Okay, let's look at the statistics. And okay, here's home sweet home. Mercury, Venus, Earth, Mars. This is our inner solar system. Got the orbital period. We're 1 year, 365 days. Distance to the star. That's 0.4 AU, 0.7. We're at 1 AU, an astronomical unit. 1.5 AU out to Mars. Then there's the asteroid belt, and then Jupiter out at 5. Here's the planetary radius in Earth units. So Earth is 1 radius or diameter, and Mercury is very small. It's 0.38. It's much smaller than Earth, as is Mars. Mars is only about half the radius of Earth. And then Venus, however, is our sister, our twin almost. It's almost the same size as Earth. And then we've got the planetary mass. And Mercury is very tiny, 6% of Earth. Venus is 82, almost same size, and Mars is very small, 0.11%. So now we come to the marketing aspect. Our culture is saturated in marketing, of course, being capitalism. So drawing these pictures here, now the uninitiated would look at this and say, oh, wow, they've got pictures of these planets. Not really. These are artist conceptions. Very misleading. I disapprove of this sort of thing. I would have put circles there without colors and all. This is fantasy. But these numbers are true, so let's focus on those. Here's the orbital period, 1.5 days. These are very close. Now, this star is a red dwarf, which is probably the most common type of star in the universe. Maybe at least half, maybe 2/3 of all stars are red dwarfs. They're tiny little stars. The reason we're so uncertain about the fraction is because they're hard to pick up. They're very small. They're faint. So we don't even know for sure how many are in our immediate neighborhood. There may be, the closest star to us is Proxima Centauri, right? It's 4 light years away. There may be a red dwarf closer than that, but we may have missed it already so far. But at least half, maybe 2/3 of all planets are red dwarfs. This particular one, TRAPPIST, is about 1/10 the mass of our star. So it's much smaller. Now you'd think, well, that's kind of insignificant then. Well, in some ways, but it turns out that because you're small, you're cool. Our star is roughly 6,000 degrees Kelvin. TRAPPIST is about 2,500 degrees, much cooler. Cooler means you burn your nuclear fuel at a much slower rate, so you live a lot longer. Our star is currently 5 billion years old, expected to live to 10 billion years. It's lights out for us, though, long before that, and because the sun is steadily getting hotter. As it slowly contracts, it moves to higher fusion rates in the center. It burns different fuel. First you burn hydrogen to helium, then you burn helium to something else, and so on and on. But so the star slowly heats up over time. And it's about 25% hotter now than it was at the beginning. In a half a billion years, about 500 million years, it's going to be hot enough to burn off the Earth's oceans. And then it's lights out. Over for life on Earth. 500 million years gives us a lot of time to do something. But it will come to an end. However, a red dwarf can live for 1 trillion years, 100 times longer than our yellow star. The universe is only 14 billion years old. So there will be red dwarfs that are currently existing, that are still burning at the end of the universe, whenever that is. Whether it's expanding or going to contract into the big crunch. The red dwarfs will just go on and on and on. Now you'd think, well, that's good for life, right? It gives you a lot of time to evolve and do things. So that's a favorable point. Okay, so here's the system. The orbital periods range from 1.5 days up to about 3 weeks. And the distance to the star, now here's where it gets interesting, 0.011% of an AU. Now, Mercury is about 40%. This is way inside Mercury's orbit. In fact, the outermost one here is 0.06, only 6% of an AU. So that's about 1/6 of the distance to Mercury from the sun. But remember, it's a very small star, very small planets, very compact, cute. Yeah. These are to scale, and these are also to scale. So the sizes are right. It's the colors. The drawings are wrong, but they are. Oh, yes, they are. Yes, they are. This is Earth. That's an Earth size. Okay. Sorry. Repeat the question. The question is, are these planets drawn to scale? And the answer is yes. So you notice, here's the remarkable thing. 1, 2, 3, 4, 5, 6, 7. They're all about the same size. And as far as we know, that's it. I mean, we may have missed one or something outside, but there are Jupiters, no gas giants, no ice giants. There's nothing like that in this system. It's a bunch of Earths, 7 Earths. Now think about it. if most of the stars in the universe are red dwarfs, and if this is a typical, this is the first one we've seen, the planetary system. They've just discovered a second one. I don't have any data on it yet. That means most of the planets, I mean the vast majority of the planets in the universe are just like Earth. Nobody expected this. Nobody. It's crazy. It's totally crazy. It's a shocker, and it's very favorable if you're interested in finding life, because we think Earth is a good place to find life, since that's the only thing we know about. So, distance to the star, very close. The planetary radius, 1.09, 1.06, these are in Earth radii. So, I mean, they're essentially Earths, and you can see by looking at them. This one's a little smaller, 0.7. That's the smallest. It's still 3/4 is the radius of Earth. And then you've got the mass, again, all approximately Earth size, this one. Because the way they determine these masses is when they're orbiting the star, they pass each other so closely together, they perturb each other's orbits slightly when they go by each other. And by the amount of perturbation, they can determine the masses very precisely to like 1% here. So we know the radius precisely from the shadow. We know the mass precisely from the gravitational neighbors. Except for this one, and we'll know this in about 2 weeks. So stay tuned. It's probably like the rest. It's probably, yeah. Okay, question, what's the size of TRAPPIST compared to the sun? It's about a tenth. I think it's 11%. So here's the sun, here's TRAPPIST, a tiny little thing. And then our stars our planets are way out here. Here's TRAPPIST, and its planets are right here. Very, very compact, like a toy solar system. The planetary mass, okay. Yeah. Question? Yeah. Good eye. You mean the ratio of these two numbers. Now, that's a good point. These two numbers allow you to calculate the gravity, and I'll come to that in another slide or two. We'll come back to that. But you see, they vary, but they compensate for each other. As you get bigger, you tend to be more massive, but you're also farther from the center of your planet, so the gravity gets weaker because of that. So you can actually change things over a fair range and still keep gravity in tolerable ranges where you don't get crushed and you're not floating away. So, okay, the comforts of home. I've thought of these as the main. What do I want? What do we want? If we go to a planet, we want to live there. What do we need? We need a reasonable temperature, right? You know, many of these hot Jupiters and so on they found are thousands of degrees, 2,000 degrees or something. That's not going to work. They're frozen solid. That's not going to work. We like temperate. We like Maui. Yeah, that's what we're looking for. We're looking for Maui in space, really. The gravity, again, we'll come back to that, but it's and then the atmosphere, vital ingredient here. You've got to have a we'll come back to that, but that's important. Radiation shielding, that can be a showstopper. If you're getting bathed in heavy UV radiation, we're protected by the ozone layer. Still, because fortunately we canceled CFCs 20 years ago, and the ozone has started a big hole in our ozone layer. It's going to give everybody cancer. And then you've got X-rays, particularly on M dwarfs. They tend to put out X-ray flares, especially when they're young. The first 500 million years, they're very excitable, and then they calm down for the next trillion years. But it's kind of touch and go the first 500 million years. They put out a lot of UV, X-rays, solar wind, and then is there life there? Now, it's not clear if that's a plus or a minus, because that life is not going to be like us. So we'll come back to that and talk in a second here. Okay, so I lumped the first two together. Let's go through one by one. Temperature and water. These are the same thing, really, because we think there's water everywhere. So if the temperature is right, then there's probably water, probably lots of water. We've now found, they found out for decades the moon was bone dry. Now we know even the moon has 1-2%, something on that order, of water in all the rock. And in the southern craters, subsurface, that's on the surface, but subsurface there may be more water. In the southern pole on the moon, there's deep shadowed craters where there is apparently deep ice, water ice. makes it much more of a habitable place. If there was no water, then you'd have to take all your water with you. If you can find water wherever you go, then you've got water to drink. You've got rocket fuel to get home again. You split the hydrogen and oxygen up, you recombine, you got your rocket fuel. And you have air to breathe. So water, actually all you need is food and water, right? So you're halfway there if you've got water. Now, of these 7 planets around TRAPPIST, the outermost is at the edge of the habitable zone. The habitable zone is defined as where you can have good water, where the temperature is right. That's all it means. In our solar system, it runs from just outside Venus to just inside Mars, or maybe even includes Mars. So we almost had 2 habitable planets in our solar system, but just missed it. Now, TRAPPIST has at least 3 in the zone, in the habitable zone. Numbers 4, 5, and 6. They're called, the star is called TRAPPIST 1A, and then the planets are called B, C, D, E, F, G, H. But I'll stick with numbers just because you don't get confused. So planet number 7 is just outside the habitable zone. The last 3 planets are in the habitable zone. The inner 3 are not. However, the inner 2 are almost certainly tidally locked. That means they always keep the same face to the star as they go around. And the others are probably tidally locked, but maybe not. They may be in spin-orbit resonances, which allows them to rotate. Like our Mercury is in a 3 to 2. It rotates 3 times when it goes around the sun twice. So it rotates, well, that's that. It rotates 3 times, it goes around the sun twice. And these planets may, the outer ones, may do something similar, in which case they would be spinning more often. And that's an important point. How fast they're rotating has to do with whether they have tectonic plates and so on, whether you have a magnetic field. Yep. Exactly. That's exactly right. If you're tidally locked, you've got one pole, the near side is going to be baked, and the far side is going to be shrouded in ice. So initially, that was one of the reasons people dismissed M dwarfs. They said, well, that's not going to be good. Even if there are planets there, they're tidally locked. It's going to be a hellhole. You don't want to go there. Not so fast. I'll come back to that in a second. Now, they think maybe these planets were unlikely to form so close to their star. They probably formed outwards. They are all 7 in orbital resonances, so they're in low numbers. So if you noticed on the statistics there, the distances out are each about 50% higher than the previous one. So it's like 1, 1.5, 2 1/4, and so on. All the way out, they're pretty much 1.5. Each one is 50% farther than the one inside. That's a logarithmic scale. It's not the same distance, not equal spacing, but it's equal spacing in log terms, right? If you take the power, it's equal fractions. And so they started out, and then because they're all in these orbital resonances now, that indicates that they may well have formed much further out, and then they migrated inwards. Something similar happened in our solar system with Jupiter. It moved in. It transferred its orbital momentum to the Saturn, mainly, and the other 2 ice giants. And so it came in closer to the sun, and the other ones went farther out to conserve angular momentum. But that's when all hell broke loose at 600 million years from the beginning of our system. They call that the late heavy bombardment, because when Jupiter moved in, Saturn was moving out, they finally hit a 2 to 1 resonance. That magnified the perturbation immensely on the other planets, caused a shower of asteroids into the inner solar system, bombarded the Earth. So we took a huge pounding. There's still evidence on the moon, you can see that. So that's the late heavy bombardment. Something similar may have happened here, and if that's true, then it increases the likelihood of water on all these planets, because there's not much water close to the star usually. It's usually farther out. It's too hot close. And so if they formed farther out, they might have had water to start with. Then they migrated in, brought their water with them. The other way you get water is after formation. you get this late heavy bombardment. All these asteroids and comets come flying in, asteroids and some comets, and then they bring water. So there's still an ongoing debate about Earth's water. Where did that come from? Was it here at the beginning, or did we pick it up later? Debate goes on. Now, okay, now back to this tidal locking. That may be a good thing because, like you said, it's hot on one side. Here's the sun. This side is baking hot. This side is ice cold. Somewhere in between, there has to be the Goldilocks zone, right, where there's perfect temperature. There's room temperature for water. Somewhere around the equator there, probably. They call it the terminator, that line. That's where the light, this side will always be bright, this side will always be dark. But at the terminator, the temperature is going to be right for water. So if there's water, it'll be liquid there. So you could have a ring ocean around this planet. Very weird concept, huh? This side would be bone dry, this side between is this ocean. Now that means even the close planets that are tidally locked could have this ring ocean around. So now you see the basis for saying that all 7 of these planets could support life, even the ones that are tidally locked. Turns out tidal locking is a good thing. And you may get the Terminator belt ocean. How's the time, JD? How's the time, somebody? We half hour in? Okay. Okay, let's talk about gravity for a second. Now, you all remember this from high school physics, right? This is the #1 equation you learn. This is Newton's force law. Force equals mass times acceleration. That was a change from Aristotle, who said something like force equals mass times velocity. And that was because he watched a chariot race, and the horses are going full force, and the chariot goes at a steady speed. So he thought, well, the more force you have, the stronger horses, the faster you go. And that's that. Force is proportional to velocity. But he was neglecting friction, of course, because you're burning up a lot of that energy in friction. So Newton finally figured it out. This is the correct equation. Now, that's his general force law, but then we have the gravity force. Newton did a number of things. That's why he's Newton. And so this is his gravity force law. The particular force that's gravity is this constant g. That's just a number. That just corrects for the units, the system of the units you're using. So ignore that for a minute. That doesn't matter. This is the mass of the planet. This is the mass of the object on the planet, little m. And then you divide by r squared, the distance from the planet. So for instance, now let's do a little algebra here. Let's set this force, F equals this force, this term here. So let's put this on the F side, and then we have, you notice, a small m there and a small m on both sides. So we can cancel those two, right? And we'll get this equation. The acceleration is then just gm over r squared. Again, we ignore the g. That's constants. So it's just the mass of the planet divided by r squared. Very simple. Now, we had our statistics. Somebody commented on this. If you know the mass and radius, we can now calculate the exact gravity. Is the gravity suitable on these planets? Well, it's important because on Earth, this acceleration, we call it 1g. It's about 10 meters per second. That means if you start from 0, you let go. After 1 second, you're going to be moving at 10 meters a second. After 2 seconds, you'll be moving at 20. After 3 seconds, 30, and so on. So your speed linearly increases as you time goes on. However, on Jupiter, we have 25 Gs. You'd just be squished flat there. You couldn't live there. Okay, let's do the calculation on TRAPPIST for the 7 planets. And 0.7, 1.2, 0.7, 0.7, 0.6, 1.1 essentially, and we don't know this one yet because we don't have the mass exactly. But what do you notice about these? These 3 are in the habitable zone. They're all either Earth gravity or less. Slightly less, too, only slightly less. So you'd be Superman there. You could run super fast, be super, you could pick up barbells that you couldn't pick up on Earth, slightly. Anyway, it's remarkable that it's how those two things compensate for each other. So the gravities are all suitable. No showstopper there. Okay. And then we have atmosphere. two words, Venus. 90 bars of pressure. You will die. The constituents on Venus, carbon dioxide, mostly there's sulfur dioxide, there's sulfuric acid, clouds. Not good. I want to even mention the temperature on Jupiter, which is 800 degrees, I think. So, okay, that's bad. If these planets have any atmospheres like this, then it's a non-go. Now the wind, this is something you don't think about much, but if we come back to that tidally locked planet, we got the baking hot side and the freezing cold side, then what's going to happen to the atmosphere? It's going to rise up on the hot side, and the cold side is going to flow under, and the high, less dense air, hot air is going to flow on top. You're going to get this circulation pattern going around like a donut, like this. And at the surface, there's going to be howling winds. People have done calculations. They figure 2,000 miles an hour. That's not a good place to build your cabin. But those were the initial, just back-of-the-envelope calculations. When you do it more carefully, if you do a simulation, and you put in a possible ocean at the terminator, which can transfer heat very efficiently, the same way with a circulation system, it turns out not so bad. The wind might be tolerable. And in fact, that circulation will take heat away and take it to the cold side and bring it back, so it moderates the whole planet, actually. So it extends perhaps what would have been a very narrow habitable zone around the terminator. It may extend it quite a bit, so it may be a sizable fraction of the planet now. So wind, not so bad. Atmosphere is so far is troublesome, though, because we don't know the pressure and we don't know the constituents. We will soon know. Actually, we know something already. We know for the inner two planets, they got light through the atmosphere as they occult the star, and so they determined that they are not hydrogen-based atmospheres like we have on Jupiter, like the gas giants and the ice giants. Not that kind of an atmosphere. So there is reason to believe that it's similar to our terrestrial atmosphere. I mean, no, I shouldn't say that. At least it's not a gas giant atmosphere. So it may be suitable. Hopefully it's not like Venus. Okay, radiation shielding. Now this is a tough one because, like we said, the M dwarfs are very active their first half billion years. They put out X-ray flares. If that bathes your planet, you're in trouble. They put out a lot of UV radiation. If you don't have an ozone layer, you get fried by that. Any animals that can get cancer. And then there's the solar wind. That's what happened to Mars. It was so small that its original atmosphere, which was much thicker, got stripped away by our sun's wind, and it lost its atmosphere. So what do you need to protect yourself? Well, on Earth we have a magnetic field. We've got a dynamo. Our core, our molten core, iron and nickel in the middle is circulating. That makes a very strong magnet. When you have an electrical conductor like these metals circulating, you produce this magnetic field. And then as the charged particles come in from the sun, they feel that Faraday force law, is that right? You've seen pictures. That's what makes the aurora borealis in Alaska. They come in, they shoot down into our polar regions where the lines, so here's the planet, the lines come out like a magnet like this. So the solar wind particles tend to come out and they shoot down. That's why you see the aurora borealis in Alaska. You don't see it in Hawaii because it can't attack straight on into our atmosphere because of the magnetic field. So you've got to have a magnetic field. Now, a magnetic field depends on rotation. And then you say, well, wait a minute. You said these planets may all be tidally locked. Then that seems like that's a bad thing again. Well, true, but their periods are so short. Remember, 1.5 days for the innermost one, out to 3 weeks out here. So they're still rotating, just by their orbital motion. They're spinning every few days. They're rotating. So there is some rotation. Furthermore, they may not be tidally locked. Like we said, they may be in a spin-orbit resonance. in which case they're spinning more often than that. They might spin two or three times per orbit. So, um, so we have some rotation going on. There's a good chance of a magnetic field then. That's good. Ozone layer needs oxygen. And oxygen is troublesome. Unless you have plant life, you may not have any oxygen because oxygen tends to react with rocks. So if whatever oxygen might be there initially tends to get absorbed into rocks. And there's I don't know, in geology you've seen probably maybe the red belt. If you go down to some level, you come to this red, it's iron that was oxidized at an early stage in Earth's history when all the oxygen basically it's rust. And so oxygen goes away unless you keep supplying it, like you have a planet full of plants that keep generating oxygen. We don't know if there's any plants there. But still, there are other solutions. You can hide behind the terminator. So here's the star. Here's the star. And here's our planet. And here's the terminator right around here. And just on the back side, that'd be a nice safe place. The back whole half, but it's awful cold on the pole, so you probably don't want to go there. But just past the terminator. Now there's your green belt. Or as we'll see in a second. Well, I'll tell you. It may be a black belt, because why are plants on green on Earth? When you look from space, you see this, the famous picture from the moon they took, Neil Armstrong or whoever, and it's this beautiful planet, green and blue with some white clouds. The green is from plant life. The blue is the oceans. Green is radiation that plants are rejecting. Our type of plants absorb blue light. It's high energy photons for high energy reactions they need to do, and then they absorb red light for lower energy reactions. They reject the green in the middle because they don't need it. They want certain high energy and low energy photons to do different things to make ATP, the molecule that, let's see, to do different things. And but our solar spectrum is sharply peaked around green-yellow color. And then it comes up like this, a sharp peak in the green and yellow, and then it drops off way down in the infrared. Now, these red dwarfs are not like that. They're much broader, smoother spectrum. So plants there, if there were plant life, they would need to absorb all the photons they could get, because so they would probably be, it's been speculated, they'd probably be black. So they would not reject any light. They would take it all. That's like, give us more photons. We're hungry for photons. So imagine that, a whole planet of black trees, black grass. That's right. It'd be a band of black, which gives the lie to those pictures we were looking at, right? Because none of those were black. So the artist didn't know about this little detail. All right. Okay, life. Now, is life good or bad? If you're going to go set up shop somewhere, do you want life there or don't you? Well, you want life if it produces ozone, because that'll be a radiation shield for you. And you want that to protect you. And there was this theory some decades back, Gaia. I don't know if you've heard of it, but what was his name? Lovelace. He said, the reason Earth is so stable in period, the temperature here, is because the plant life regulates. The forests cool the surface of the ground. They make cool air, then the shade, and they absorb energy, and then they release it in infrared and re-radiate that and so on. But there was this whole idea. Now people are skeptical of that now. We're not sure that really makes a lot of sense. It was a attractive idea, but we're not certain about this. Now, these plants are going to be inedible because our life form, our DNA molecules, all life on Earth is the same basic molecules. We use 20 amino acids to construct our DNA molecules. There's there's hundreds of 100 or 200, something like that, amino acids. Why did we pick those 20? I mean, why did evolution pick those 20 to start with? Was that just a random thing, or was there some reason? Are those 20 better than the others somehow? And that's also under ongoing study and debate. So we don't know the answer. But we don't know that these 20 are anything special. It might have just been a fluke, the first cell that got going, or whatever, RNA life, whatever it was. It happened to have those 20 available, and it used them. There might be better recipes. But it's probably unlikely that planet number 7 at TRAPPIST is going to use our same 20 amino acids. If it did evolve life, it probably picked out a different 20 or a different 35 or a different 8 or whatever, So that food there is going to be inedible for us. In fact, may not only be inedible, it may be poisonous. So, I mean, hopefully you would eat it, it would just go through you, and it wouldn't do you any good. You couldn't digest it. But it wouldn't hurt you. But in the worst case, it would be absolutely poisonous. In that case, you'd probably rather not have life there if you want to set up shop. You'd rather just bring your own seeds, start your farms, get your own life going, and not have to compete with the soil that's already full of alien bacteria that are going to fight you tooth and nail, and trying to steal your resources and so on. So, hard to say. Now, panspermia, that's the seeding of life from one planet to another. Like, say an asteroid hits the moon, say it hits an asteroid, or there's not much gravity, hits an asteroid, blasts it to bits, some of those rocks fly out, eventually they will make their way to Earth, they land on Earth, we pick them up. We've found about 60,000 meteorites so far in collections on Earth. Mostly collected from Antarctica. They're very easy to collect there. They land on the snow, rocks where they don't belong. But we have a lot of most of those are from asteroids. Some are from the moon. There's a big asteroid strike on the moon. Now, they're very fewer from the moon because it's harder to get out the gravity of the moon. Even if you have a big asteroid strike, it knocks stuff out. But the moon has 1/6 of Earth's gravity, so the rocks don't get very far. They fall back onto the moon. Asteroids, they just float off into space. They can wind their way to Earth eventually. How many do we have from Mars? We've only got 100 meteorites. Out of 60,000, only 100 of them, 120, came from Mars. It's very hard. First of all, Mars is a fairly big planet. It's much smaller than Earth, but it's a lot bigger than the Moon. The Moon is about 1% of Earth's mass. Mars is 11, so it's 11 times bigger than the Moon, 10 times. And so you've got to have a big enough impact where the explosion knocks these rocks clear out of the gravity field of Mars. That's not easy. And then Mars is half an AU away. It's a long ways away. Those rocks have to somehow get to Earth. That's tricky. So very rare now. But on TRAPPIST, these planets are so close together, they think the odds of them exchanging rocks would be 100 times more than Mars, the likelihood of a Mars rock getting to us, because they're so close together, they don't have to get very far. So, now this raises a very intriguing possibility. You could have had life evolve independently on 7 different planets. They might be totally incompatible. You take an animal, a plant from one planet to the other one, it can't grow there because it's all wrong. The bacteria, everything's wrong. But then there's another possibility. They're also blasting rocks off of each other, and when they get hit by asteroids, those rocks can easily transfer. They're exchanging genetic material. If it's the case that bacteria can survive a journey through space inside a rock. We know bacteria live in rocks. We dig down in the earth, we find rocks. We find bacteria hundreds of meters deep in the ground. They're living off chemical reactions and so on, different mechanisms than we use on the surface. But and there was a lot of excitement. Just a few years ago, you probably saw in the paper about in the news, they found these features in these meteorites, and somebody said, that's a bacteria. It kind of looked like a bacteria. Now we think not, probably not. So we still have no known cases of bacteria coming here from somewhere else. But it's not ruled out. So this is a possibility. Okay, here's the comfy summary. Temperature, bingo, very good. In fact, you couldn't ask for more. 7 planets, possibly all habitable. Water, same thing. Bingo. Gravity, bingo. So far, so good. Atmosphere, now we're a little unsure of ourselves. We don't know about the atmosphere yet. We will soon. When they put up the James Webb Space Telescope, it will be able to decipher the spectra from the atmospheres of these as they pass in front of the star. We will find out, and that goes up in 2 years, I think. So stay tuned. We will soon know what the atmospheres are like. That'll tell us. That'll answer this question. We do know it's not hydrogen, so that's good. But is it like Earth? Well, almost certainly not 80%, 79% oxygen, 20% nitrogen. Probably not. But is it something we could deal with? Maybe we've got to wear respirators around or something, but as long as it's not sulfuric acid or something, we can work around it maybe. Radiation shielding. We don't know. We don't know if there's a magnetic field. We don't know if there's an ozone layer. But again, we could hide behind the Terminator. Might be able to get around that. Even if we don't have magnetic field, ozone layer, you hide on just past the Terminator. Life could well be there. On the summary, well, what moral can we draw from all this? TRAPPIST may be relatively pleasant. There might be 7 pleasant planets. I mean, it just fires the imagination. These things are so close. They would look in the sky. They'd be bigger than the moon, the full moon to us. They'd be 2-3 times the size of our full moon. And you'd see multiple of them. You'd only see 2 that are that close. They're your closest neighbors. But then you'd see more farther out. They'd be much bigger and brighter than when we see planets go by. Very spectacular view. Talk about tourism. I mean, oh man, you build a hotel on planet F, and you have a shuttle that goes to G and D and so on. It's big there. Trump should get involved, and build a Trump hotel. They're selling timeshares, exactly. And there's a Hawaii in the Terminator Ocean, and a Maui probably right there. You get your beachfront cottage. They wear a respirator maybe, but the devil's in the details, though. We're still uncertain about the atmospheres. Stay tuned. It's definitely not as nice as here. This is all set up. We've been here. Humans have been here for hundreds of thousands of years. Our ancestors have been here for almost 4 billion years. This planet is perfect for us. And then there's one other little problem. You can't get there. Speed of light is an issue. Einstein said, no. That seems to be a flat. We don't know of any loopholes. People talk about wormholes. Yeah, maybe you can squeeze an electron through a wormhole. You ain't going to put a human being through one. You can't get there from here. Never. I don't mean like we can't get there this century. I mean 1,000 years from now, no matter what our technology is, we won't be able to get there. We'll know a lot about it. We'll be able to look. We'll have vast telescopes by then, probably, if we survive. And we'll find out about these things. So it's always going to be a look, but you cannot go. Yep. Ah, yes. Okay. Question is, what about traveling microchips? Now, I said we can't go there. We might be able to send some little doodad to take a picture. People talk about solar sails, fusion. I don't know. They've got all schemes. Trouble is, when you get there, you're going, let's say you get up to some appreciable fraction of the speed of light. You're going for, it's 40 light years away. Let's say we could go half the speed of light. We can't, but let's say. That would take you 80 years to get there. And when you arrive, you're still going half the speed of light. You don't get to take pictures for very long. It's not that you stop and examine it, take movies. No, you get 3 or 4 pictures, it's gone, That's it. After 80 years, you've been waiting. So I suppose if civilization goes on for another century, 2, 3, 4 centuries, 5 centuries, we might be able to deal with something like it. We might be able to send out some. Maybe you send one after another. You take a series of pictures that way or something. I don't know. Here's another problem. People always talk about going a fraction of the speed of light, but they never mention that the fact is if you run into a grain of sand going half the speed of light, it has the kinetic energy of a nuclear bomb. you're going to run into a few grains of sand along the way. Now, in the recent Passengers movie, as you might have seen, you know, they're going to they're traveling for 100 and some years, and they're all asleep. Two people wake up by accident. That's the plot. One wakes up by accident, and then, yeah, he wants a girlfriend. But I see. Okay, they're flying along through space, and they're all sound asleep. And here we come. There's a asteroid field up ahead. Well, first of all, asteroid fields are in planetary systems. They're not out in interstellar space. And secondly, asteroid fields in our main belt, it's not like that. You always see this in Hollywood movies. It's a field of rocks, like Star Wars. You're dodging the rocks. You're flying around like a maniac to avoid the rocks. No, real asteroids is thousands of miles to the next rock. You can't see any other rocks. They're very scattered far and wide. I mean, although there are like 1 million asteroids, space is vast, even the distance in the asteroid belt, which is 1/10 of an AU. So you're not going to ever see anything like that. But okay, if you did hit something, they hit a rocket, it messes up their computer system. That's how one guy gets woken up. But that's a big rock. Now, but okay, that's not going to happen. But you are going to hit grains of sand, and those grains of sand are lethal. 1 grain of sand. Now, here's the question for the student, and all of you online. Who am I talking to online? At that camera there. Hi, folks. Go home and calculate half mv squared. That's kinetic energy of a mass of a grain of sand and going half the speed of light, and compare that to the energy of a nuclear bomb. I have not done that calculation, so you'll be one step ahead of me. I did read, though, that it's equivalent. It's on the same order of magnitude. So you can't go half the speed of light. In fact, you can't go 10% of the speed of light because of this nuclear bomb sand grain problem. So we're restricted to less than 10%. So even if we could get even if we had a propulsion system that could do that, you can't go that fast because it's too dangerous. You'd blow up when you hit something. So, in the movie, they have a force field. Yeah, they put up shields up, Captain, and shields. What are shields? That came from Star Trek. I don't know what a shield is. It's a magnetic field. I don't know. The magnetic fields aren't going to work on rocks anyway, so. So it's impossible to get there. Well, let's say we go 10% of the speed of light. 40 light years, that's 400 years. I don't think any human civilization has ever started a project that took 400 years to complete. The nearest thing I can think of is the pyramids. I think they went over several pharaohs, didn't they? Anybody here, archaeologists? How many? 20, that's all? Okay, well then that fits perfectly with my argument. No civilization that we've ever had on this planet has done anything that took more than 20 years to do, I don't think. 500. Who? Oh, the church. It's a church. Yeah. Did they had the final result in mind when they started it? Oh, the question for the online audience, the question is, counterexample is the dome in Milan. Took 500 years. Well, it didn't involve getting on a spaceship. That's what I would say. The church kept making money for centuries, and they could spend it on lavish gold domes and whatever, but it's hard for me. I mean, at least under modern capitalism, where we look at quarterly profits, it's hard to visualize anybody, and it's hard to visualize any individual getting on a spaceship that's not going to arrive somewhere for 400 years. It's not comfortable life on a spaceship, and I don't think anybody would do that. So, well, here's my grand conclusion. We should take better care of the planet we share. Thank you. I think we've got time for questions. JD, we got a few minutes? Is there a procedure for questions online? Coronado Shores, shout out to you folks. Yep. The James Webb Telescope will be able to detect the light and get a spectrum of the light through the atmosphere. But to get a picture 40 light years away of the planet, we would need a much larger telescope than anything on the drawing board now. So we'd probably need a giant telescope in space. Not going to happen anytime soon. Not this decade or the next one, anyway. Yep. Listening, yes. Okay, the question is there any technique for listening in to see if there's signals coming? Yes, there is. We have radio telescopes. And yes, they have already honed in. Where are we now? We're 1 hour later. We were there, now we're about there. TRAPPIST. So we pointed at TRAPPIST. We listened carefully. Nada. No, now if they were listening to us, 40 years ago was the 1970s. The first broadcast was I Love Lucy, I believe, in the 50s, started going out to space. So anybody within, They'd be getting Star Trek right now, but for 20 years ago, they'd already have I Love Lucy. They'd be rolling in the aisles. And is that a good thing or a bad thing if they think our highest cultural attainment is I Love Lucy? I don't know. I mean, some people would say yes. I'm agnostic on that question. But do we want people watching our TV shows? I don't know. Okay. Yeah, so, I don't know, American culture, it's, well, so, but no, we don't hear any TV shows coming from TRAPPIST at the moment. Now, that could be because they're primitive and they don't have TV and radio yet, or it could be because they're advanced and they've gone past TV and radio. We're going to fiber optics probably, and we'll go radio silent on Earth eventually. I mean, in a few decades probably. Huh? Yeah, okay, well, if we're going to, now, okay, we're going beyond space when we get to telepathic. I went out 40 light years, he's saying, so all rules are broken. If you go to a very advanced civilization, I mean, we're almost to fiber optic cables already, so pretty soon we won't be broadcasting into space. So radio is probably something that lasts. It started in, what, 1920 was the first radio, Marconi. We haven't had 100 years of radio yet. And in another 100 years, it may be over. We'll be all fiber optics, So maybe you only use radio for 100 years. It's like a primitive technology that you use briefly when you're just maturing as a technological civilization. But we've had civilization for what, 6,000 years, 5,000 years at least. And out of that 5,000 years, only 100 of them had radio. So it's 1/50th of the time of civilization. But compared to the life of the planet, 4 billion years, it's nothing. It's whatever that comes out to. So it's, radio comes and goes like that probably. So I think that whole thing of searching for radio signals is doomed because of that problem. Even if there is a civilization, even if there are civilizations everywhere, they're probably not using radios. So, I mean, it's worth looking. You never know until you look. I'm not saying you shouldn't do research, but I wouldn't spend my money on it. Yep. A questioner from Coronado Shores wants to know if NASA's research on warp drives is going to pan out. No. What is a warp drive? I mean, it's off a TV show. What's What's a warp drive? They actually have something called a warp drive. I don't think. No, my answer is no. Yeah. That's exactly the math. You did the math right. Even if there's lots, it's such a brief time. Right. Exactly. So it's a needle in the haystack. We'd never find it. Yeah. Another question. Oh, repeat the question. The question is, if there's even if there's lots of civilizations, if radio is very brief phase, then the odds are slim. And he's exactly right. You got the makings of a mathematician, I think. You're going to be good at calculus and algebra. Yes. Yep. Gravity. Yep. Oh, that was just to single these out as habitable zone. This has nothing to do with the gravity. That's just these are the three that they say are in the official habitable zone. But as I said, the others could be habitable. Yeah, for the other reasons we talked about. The gravity is very suitable. That's the startling thing. I'll confess, I did this. I started to work this up at the beginning, and I did the calculation wrong. I plugged it into Linux, and I was getting gravities of 2 and 3 and 4 and so on. I thought, oh no, there's the showstopper right there. But then I did it right a couple nights ago, and they're almost the same as Earth. It's remarkable. I mean, this is Earth's in every way that we know about, except for the atmospheres, which we don't know about yet. So nobody expected this. You know, like I said, the M dwarfs were initially ignored in planetary searches because they were considered not suitable. But I think the first person to say that that might be wrong was Jill Tarter. You've seen that other sci-fi movie, Contact? I think Jodie Foster plays the Jill Tarter role. And the real astronomer, Jill Tarter, said, she wrote a paper and saying, well, wait a minute, let's look at M dwarfs a little more carefully now. You know, because of you can hide behind the Terminator, maybe the X-ray flares aren't so bad. What if there is a magnetic field, you know? And so, oh, I mean, the first thing was they figured anything that close would be tidally locked. Well, now we fought it over, and you realize that may not be a bad thing. It might be a good thing. Even planets outside the habitable zone could still have bands that would be nice places. That band ocean might have an island in the middle of it, might have surf beaches, sandy beaches. I mean, it's going to be just like our islands, you know. Very moderate hula dancing. Yep. True. Exactly. Exactly. It's okay. Question is, if you have this civilization at TRAPPIST, it can move between these worlds easily. It'd be like us going to the moon, which we can easily do if we want to spend the money. And so then you have a lot of resources. Each planet is going to have slightly now. In one sense, a planet is a planet. You're going to have sort of the same thing on every planet. You have rock, water, hopefully. Probably standard issue rocks, you know, silicates and such. But as we know on our own planet, there are certain places where you have certain things. In South Africa, you got diamonds. In Canada, in the Sudbury Plain, you've got a lot of platinum and iridium from an asteroid strike there. Dumped it there way back. So there are hot spots on the planet. So there might be one planet with a lot of gold and another planet with platinum laying around and so on. And you want to go and collect all those things to use for making iPhones or whatever. You know, so So yeah, that would be an advantage. It would give them an edge. Well, an edge. We're assuming we're describing this as a competition, which it's never going to be because there will be no war between these worlds. Now, there's another problem. If you have, but then there's another problem. Like I said, if the evolution, if the life evolves independently on each planet, then you couldn't eat the food. So you could go there. You might not be able to breathe the air. The atmospheres could be quite different, or they could be similar. We're totally in the dark on that. But it's just fires the imagination just to imagine this 7 planets like Earth in a row and right going by. You know, like they're all over. All right. If there's no more questions, thank you. Oh, one. Here we go. 1.5 billion. Well, not. Oh, maybe not a million. I mean, let's say we could get a long time. Yeah. 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 No. Yeah. Right. You'd think that, but you know what? What's the practical benefit? Well, what it made me think about was at first I thought, wow, you have this reaction. Look at this, you know, it's a gold mine. What a place to live, you know. And then you start thinking about issues, about the details, and it's like, well, maybe not. So that brings us back to this, the conclusion there. Maybe we have to think about distant planets to actually put our own planet in perspective. This planet is nice for us. It's perfect. And we are trashing it. We're destroying our atmosphere. We're heating up. I mean, the last 4 years, the temperature is going nuts. We are heading for a catastrophe. So now I know, I don't want to offend anybody. I know these are politically sensitive questions. There's a lot of money on the line. Fossil fuel companies don't want to hear about climate change. But it's a reality, and in the past, scientists could afford to stay in the ivory tower. We're past that point now. We're in trouble. We are facing a crisis on this planet, and we have to act soon. Right now, we need to act quickly to avert a catastrophe. And so scientists cannot afford to be disengaged observers anymore. We have to get out. There was a recent big march about the March for Science. I don't know how big it was, but you're seeing climate scientists. Before, they would just write their academic papers, put them out. They didn't want to involve in politics, partly they don't want to get their heads on the chopping block, you know. But we can't afford to play it safe anymore. I think that's maybe the main benefit. It makes us think about our own home and value it properly. Thank you very much.